So, Tim Ventura from Alt Propulsion here with Isaiah Ritchey for a lab walkthrough and all of the latest and greatest. Sir, you have been busy as heck. I am so appreciative for you having me down.
You're welcome.
So, yeah, I guess start us out with a lab tour. What's going on?
Oh, so much has been going on. I mean, ever since the last video a while back, it's just so many developments, but mainly in the research and development of magnetic fields and putting sine waves onto magnets. Really started with a hunch, and now it's turned into something that is a repeatable process. So let's see, if we can go over here, I'll bring a few of these. I'll bring this, because this is kind of the math portion I wanted to show before I break into it. So this is law of squares. This is one of the things John used to make the SEG using this type of math. And this has to do with the weights of the rollers. But one of the things I'm trying to do is put a frequency onto my magnets, 136 hertz, because according to law of squares, when you add these all up, you get 136. And no matter which row you add, you always get 34. So that's basically been the last year and a half of trying to get that onto a magnet, 136. So far I've gotten 34. There have been quite a number of iterations on the design of the magnetizing systems. Finally led into this, it's not the final prototype, but this working module, which I could put 34 very clean sine waves onto a magnet. This is probably about the
Okay, so that is the magnetizer then?
Yeah, one of the coils that works repeatedly over and over and over, doesn't burn out, doesn't overheat. It just runs and runs and runs. I can do, so far I think I've done about 20 rings, the same exact patterns in every single one. It all has to do with a specific geometry put onto these magnetic rings, but these are basically a lot of the first prototypes. They kind of look like a nautilus shell, but they're real, the geometry has to be very specific. So you have 34 points around here, just like you have 34 whenever one of these grids is added up. But each one of these is not just straight through at 90 degrees, it actually angles at 21 degrees. So let's see, I can show a little bit cleaner version so you can understand what's going on. Excuse the traffic. So these are some of the earlier ones. Basically, they would be a one-shot approach. They work once and blow up and leave a pattern, and you have to spend 8-10 hours building one more.
So you're using these to magnetize a sine wave into the rollers then?
Correct. Yeah, you take the ring, like a blank ring, pre-magnetized, and the ring would fit pretty tightly right in here, making near direct contact with these coils. So these first ones had a lot of bugs and issues, but they would fit right in here. The one thing that it would be a lot of trial and error and hit and miss with these, because what I didn't realize at the time is the magnet in relation to the current had to be one specific direction. If it was flipped the wrong way, no patterns. Flipped the correct way, lots of clean, nice patterns. Also find out what type of voltage to use. If I use too much, it basically washes out the pattern or basically destroys the field. Not enough power, and you get very faint impressions. But what I found with these neodymium rings is about 2900 volts is optimum. Maybe 2850 to 2900 is the perfect current or a voltage for these rings. And the same with this, is just the same voltage. And for this one, for instance, I created these jigs so that you would put this down and then put the ring in with let's just say the south side up. And then you would just hook this up to the terminal and charge up the capacitor bank, hit it, and out would come.
Okay, and so at 2900 volts, you've got a lot of current flowing through that then. That explains why the other ones blew up.
Yes, exactly. And cross wires or too tight of a bend, it would loosen up the protective coating on the wires. A lot of different bugs. So yeah, I went through a lot of iterations, and this whole process started this January of discovering I could actually imprint a wave onto a magnet. It was kind of a hunch and an accident. But from there, I've just built and built and built. But the geometry, which is amazing, let me get my jig and show you. So some of my first iterations was putting this module together to where it's 8 layers tall, so you could have the entire roller could fit in, and then you would wind it with the copper wire going through here. Not just plain bare copper wire, but the protected enamel. And so this would be the base, that would be the top. But after the first few times I wound this, I realized with this geometry, 34 points, 8 layers thick at 21 degrees, when you would put the wire through here, it would create this beautiful like whirlwind of, or twirl, I should say, spiral, that's the word I'm looking for. And what it would do is you would put the wire in here and it would come out directly 180 degrees at the other side.
Okay.
If you did 7 segments, wouldn't work. If you did 20 degrees, wouldn't work. 34 points, 21 degrees, 8 segments tall, you get this perfect 180 degree twist. So the field twists 180 degrees. That was a shock to me. No one had ever mentioned that before, never heard it anywhere. It was one of the things I discovered. When you only stick the law of the squares using this math. So let's see, what is that? Magnet film.
So one of the things that we were talking about before we started recording was, so the Searl Effect Generator itself is very complex. He had a lot of special, basically materials in rings within rings, right? Yes. It's a very complex idea. But then what's even more interesting is the magnetization is so complex, and basically you're putting a sine wave onto a permanent magnet, right?
Correct. And as research has progressed, even in this last month and a half, what I'm finding is 34 points is only about 1/4 of what I want to do. What I'm working towards right now is basically on the magnet ring, and also use the demonstrator unit here in a little bit to show that I need basically one big peak on the magnet ring, and so basically instead of 34 points, it would be one big point and all the rest would look flat from the surface, but there's actually, it acts as a carrier wave for 136 smaller waves. So it's basically waves within a big wave. And what I found with that one big point, which I can show, I have the magnets over there, with that one big point, it creates like a big spring effect on the magnet. And so it will jump and launch ahead. And so on the one wave going around the magnet, you would have very small impressions that you could see with magnet film, but better with an oscilloscope. 136 points, just like as in the geometry, and then one big point. So that's something I've been able to produce, is the one big point, and I'm also now working towards the 136. It's going to be a little challenging, but I do have several magnetizing fixtures already in the works of building towards them.
Has it been surprising, as you've learned about this, how much detail went into the design?
Yeah.
And I guess the other thing that I would ask that's intriguing is Searl put out these incredibly detailed schematics years ago, and he made lots of predictions about you should see this when you do that. Has any of that come to pass? As you build this, are you seeing little bits and pieces fit into place in your head?
Yes, and particularly even recently with the spinning up the copper stator, a normal magnet will not catch and spin like a magnetic bearing unless there's a wobble to it. So if I put a wobble in this wave, like the wave field on normal magnets are perfectly straight. Well, when you spin them up against copper, the copper spins, but the magnet will just remain stationary. But if you let it oscillate, go back and forth, it grabs it and pushes it and propels it. So when I put a magnetic wave to copy that wobble, the ring will spin.
Ah, okay. Yeah. And so you have to magnetize not only the small rollers, but you have to do the large rings as well, right?
Yeah. They have to have, so everything's kind of like in relation from the stator to the rollers, those are oriented at like 90 degrees. And so I'm really focusing mainly on the rollers, getting them squared away to understand the process and make it repeatable, just as this is repeatable over and over and over and over and over, and it doesn't break, and I can do the same patterns over and over. Okay. I love that. But once I get to that 136 hertz or points, Then I'm going to move into the magnetizing the stator, because those are a little different, because as the roller goes around, it has to relate to the stator in a different manner compared to other rollers.
Okay.
Yeah.
But really, you could come up with like 3 jigs, more or less, right?
Yes.
So you have one for the rollers, and then you have one for each of the stator sizes.
Exactly. Yeah, I've drawn out plans for those to basically, same as like with this, you just slip it into a jig, push the button, get your patterns. The same I'm going to be working towards, and I have a few designs for the stator magnets where you just take out the stator, it's pre-magnetized, and you take out that stator magnet with the correct orientation up and put it into the jig and push a button. Now there is, as I'm going on with this, learning more about Floyd Sweet, which his work parallels Searl's, there is a conditioning process which I'm learning about to find the frequency response range with magnets, which I found that last night. And also being able to change that frequency response to be the frequency response I want, which is 136 hertz, not 18 or 20. So I modified a magnet, one of them, and I got a frequency response of 30 hertz. So that was very encouraging to see I can alter it. But now the thing is, I want to alter to exactly where I want it and lock it in.
Yeah, amazing, amazing. So again, you are taking, I mean, this is decades of dreams that you were realizing here. And
18 years
absolutely
now,
amazing. And I guess I should do a shout out to people like Jason Verbelli, as well as some of the other Searl builders who are out there, right? Who are some of the folks that you've worked with on this?
Oh boy, well, first right off, 2 main gentlemen that are the biggest contributors to this. Jared Yates and also Josh Varner. I know they're both seeing this, and those 2 are a godsend. Those 2 have been the greatest asset to this the greatest contributors to this project. Without it really, I probably would have just closed up years ago and stopped. I really was at that point.
Okay.
And then Jared and Josh came along, and it's just this work has accelerated because of teamwork, because of effort, because they're contributing. Those 2 have just been fantastic allies and friends.
Yeah, yeah. Well, and the reason I mentioned Jason earlier was there is an existing history of people doing design who have expertise, and that's something you've been able to draw from as well.
Yes.
So.
Every little information I found on the net, and then personal correspondence with Jason, and some with Fernando Morris. I mean, Fernando was the one that he broke ground on the Searl effect. He's the one who brought it from just a kind of a concept or something out there like an urban legend into reality.
Yeah, I saw a video of one of Fernando's replications years ago.
It's the best.
And so again, it's what is so exciting is to see you picking up the torch and carrying it for this. You know, I mean, there is such a tremendous legacy of interest as well as past work that's been done in the Searl Effect area, and you have picked that up and you're taking it so much farther than other people. So do you want to show me over there what the rings look like?
Yeah.
We were getting into the magnetization process.
So this is the gizmo. This one's only about a year and a half old. I finished, well, not a year and a half, about a year old. I finished this up last summer. There's only a couple rollers. Let's see, there's one over there. Oh, there's, I think, one here. Where's the other one go to? Oh, here. So these were 2 prototype rollers I did last year. This one, I was experimenting with sprocket magnets, which had a lot of success. I was following the work of like the Rustin SEG, so you could see the holes I drilled under. I did these all underwater. And so you have magnetic fields going this direction, and also magnetic fields going outwards. And then this one, let's see here. Oh yeah, that's another one I need to show. It was last year, I don't even remember what started was like about a project about 12 years ago, which started the whole idea of being able to modify these magnets to put wave field impressions, sine wave impressions. And earlier last year, I was literally cutting into the magnet at 21 degrees and putting extremely small diamond cutting tools, but they're very, very thin. And so I put these super, super small slots into the magnet, and that would twist the field and make it a sine wave. But I got to the point, like, that's not the way John did it. And cutting magnets just seems like a very archaic mechanical way of doing it instead of like going in there and changing the field itself. There's just the goal I wanted to get to. So that was kind of like the precursor to the actual magnetizing I'm doing, was setting up jigs and cutting slots. So this was one that has all these slots, and I think, yeah, they're pretty faint. But in the film you can see the angles, but it didn't really change the fields around too much. They're pretty faint. As we're like with this roller, this has all the perpendicular magnets, and it's real easy to see this one. So all the fields, they have the main fields going up and down.
Okay, so these are the magnetic fields that are embedded into the roller itself.
Mm-hmm. And this is very similar to what the Roshan and Godin project was, except they only had a top band and a bottom band that had the sprocket magnets, as were mine were all 8 layers. Let's get this film here. So I put together some jigs here to show. So that's one. Oh yeah. So these are ceramic. One of the discoveries I made, which I'm kind of torn between keep using neodymiums or ceramics, because the ceramic magnets, they're so easy to change the fields. I found I can change these fields at around 250 volts. Their density is much less. Neodymiums take 2,900 volts to change them around, to orient them, as where these ceramics, it's child's play to be able to change the fields on these. Very, very simple. I think it's this one. Oh yeah, this one. So this was one of the very first trial runs. I tried it with 1,500 volts, thinking it would take the same amount of voltage. So it blew holes in these. I think they're called magnetic bubbles, maybe. But it put some really pronounced fields on here, and it had some pretty odd effects. Sometimes these things act like they vibrate on the platform, on the steel platform, for a little bit.
Okay.
It's pretty interesting. And as with this one, this is not a perfectly complete one, but this has like the sine wave patterns. That's not a super clear, but this is one of the first ones I did, so it kind of came out sloppy there and there. The testing platform I use is this guy. So this is a Gauss Tesla meter, and you hook in a ring sample here, a ring segment, and then this is a Tesla probe that connects to here, and this has an output which goes to the oscilloscope. So electrically you can see those wave fields. You can see how many peaks and valleys you have, if you need to add more or take away, the amplitude. And I'll show that running out in a bit, but this is one of the modules I was talking about with the bearing effect for the magnets. So I put together.
Okay, and let me move this one over here. Okay, and then I will come over here.
Okay. Let's see. So this one has. This was pretty blotchy. Where it is? Oh yeah, that was that single one. 33 points. So this is one that came out pretty good. This is 33 points, just 33 points. I think that was on the repeatable one. It got a little sloppy.
So one thing I'm noticing is the Searl Effect Generator is very smooth and polished looking on the surface. Mm-hmm. The complexity is the fields that are embedded in it.
Correct. It's like the software and the hardware.
Yeah.
Yeah, you can have the hardware all correct, the weights, the sizes, everything. But if you don't have the software right, it's just a nice paperweight. And this one, I did 17 points. Yeah, they're not as pronounced because the copper layer is on there. But this was half of 34 was 17. I glued the copper cylinder to it, so it's not as clear. And this was an experimental one. Okay, so I'll turn this thing on. So this is basically reverse action instead of the roller spinning, the stator spins to demonstrate the eddy currents. What are you doing? Should have put a shim under here. There we go. Okay. So what I found with a normal neodymium magnet is if you get a wobble to it, the eddy currents on here will grab hold of that and make it spin. So if I just wobble it while it's spinning, I don't need to touch this at all. But if it goes perfectly straight, you won't get any motion.
So these are the embedded fields that are creating that spin.
Well, this one actually is a normal magnet, but the only reason it does it is because it's wobbling. So when you put a field that goes up and then goes down, it will grab hold of it too. So that's just the demonstrator. So, like if this one stays perfectly straight and true because this is wider, so it has no wobble to it. So you cannot get that to spin without the wobble. I mean, I can hold it and everything, but it won't continue it. Eventually it just slows down. But if I bring a wobble to it, and there it just stops, which is normal.
Okay.
So that's one thing I've learned is like, I used to think you just have these nice spikes and that would grab hold of it, and it doesn't. It needs to actually have a waveform where it goes up and then it comes down and then goes low and then circles back around and then builds up and then goes down.
Yeah. Well, and the reason I keep reinforcing that is this is something you've said to me over and over is Searl is embedding sine waves into the rollers, into the stator, right?
Yes.
And so again, it's deceptively simple looking on the surface because you see that smooth ring. What you can't see is the fields, and we had those under the magnet film a moment ago.
Exactly, and that's what kind of reveals the underlying, not secret, but the inner workings of it.
Yeah.
Yeah. This one has 33 points. As long as it gets a wobble in there, it spins nice. The wobble's only made about a 1/16 of an inch plus. So this one has, it's what I was told in a dream from Searl, to leave 33 points and one empty. So 34 total slots, but one of them is empty.
Okay.
And so I followed that. Even with the jigs, I left one empty. So as long as it gets a wobble, it'll act like a magnetic bearing without ever touching. I wish it would float above the surface, but I haven't quite got it to do that yet. It's real close. And this one's spinning at 885 RPM. So that's one of the things to learn is just you have to have that wobble in the wave. Otherwise, this nice straight wave, nothing will happen at all with this. Let's see, and then say for this guy, this will probably take a second to turn on. Yeah, so let me show the ring first before I do all this. This will take a moment to turn on. I did this ring a couple of days ago. It was just to put a nice peak on there. Not like 33 points, but just one big peak. And so this one was a strange one. It came out as a square. That was a bit of an accident. I've tried doing square waves in the past. I could never get it. But this one came out as a square. So that's not ideal what I want, but kind of a byproduct of the research. But one of the things I've found with a peak is it has a nice compass deflection.
And so this is the oscilloscope. You can actually measure
Exactly.
You can measure that embedded wave in an electrical way.
Exactly. Let these settle down. Yeah, even from about 3 1/4 to about 4 inches away, it deflects the compass, and it deflects the compass under here. So I'll rotate this segment. Actually, I'm going to keep this way. My watch throws it off sometimes. And first, I'm going to reset this back. There we go. So this is the Gauss meter probe, and it connects into here to take a reading, and this has an output. This is the one model I love because it has the output to the oscilloscope. Let's see if I can back it out. And so you're able to track the waves as they go. So that was the big peak I put on there, and it goes up, and it'll cycle around, and it'll drop down.
That's amazing.
Yeah.
That is so cool.
So I can do this with...
So let me focus in on the ring. So that is the ring, and what is being measured on the scope is the embedded field.
Yep. Now if you get a normal ring, there's not really much that's going to show at all. It's just kind of a flat, even line, which is normal for the magnetizing process. Ah, yes, this one. This one's 33 points. Now in the long run, I'm not going to go with these kind of rings because as research has been going, it's what I'm looking for is one big pulse, but a micro amount of rings inside that entire wave. Let's zoom into it. Is this negative? Oh. So that one's not as pronounced as obviously a neodymium. And that's milliteslas.
Ah, okay.
The waves are quite small. That's increasing. There we go. So you get a lot more smaller ones, like these little ripples.
I see. Okay.
They're definitely not as pronounced as the neodymiums. The other thing is there's no big pulse on this one. It's just a lot of ripples. What we're ultimately going for, Josh is working, and he developed it yesterday, is creating our own magnets from scratch, and he successfully did one with a barium magnet, which is, I'd love to be able to do is work with barium magnets. They're out of, you can't buy them anymore, unfortunately. You can make them, but basically all the ones that are created today are strontium magnets, ceramic magnets.
Okay.
And there's something very unique about that barium mixture, and that's one of the type of magnets that Searl used back in the day was barium, and it has something very unique about that element.
Interesting. Okay.
Barium.
Well, and one of the things you'd mentioned earlier was that you were looking at possible alternatives for neodymium, right? Because it's from what I recall, it's very difficult to machine. It is very difficult to work with, and it's of course super expensive.
Super expensive, very flammable, very dangerous to machine because it's a rare earth product, and you got to have it inside of a chamber filled with argon or an inert gas, because when you're grinding it, cutting it, anything, it produces a ton of sparks. Plus it oxidizes in the environment. So when you're not using it, you need to have it in a vacuum chamber. So right now it is an area of research of trying to find a replacement for neodymium. And so far, one of the ones, we haven't tested it yet, I want to get bigger samples, is this is what's it called? Mesh metal, or ferro rod. I bought these off the internet and just chopped them to size to basically they would go inside of the roller. This is a little too big, but they would go inside the roller and be the neodymium replacement, because according to the stats, they're about 85% rare earth mixture with a little bit of iron thrown in there. They're like a 15% iron binder, but they're very soft to machine. They spark like crazy, so whenever I grind them or cut them, I have to use lots of water. But I was able to saw those, machine them with water, and I could do it. So it was very nice, and they're very cheap in relation to neodymium.
Yeah.
Very cheap.
So has the technology in general progressed in a positive way that helps this? And the reason I ask is a lot of the stuff that he worked with was kind of heavy-duty materials, right? Which may not have changed that much since his day.
Not really much. The only real big update we're working with is he was nylon 6/6 for the insulator material. Right now, Fernando used it, and I'm using it as Teflon. I wish they made a 3D printable Teflon right now, but they do make printable nylon 6/6. So that's an alternative we're thinking of going to do future models, especially the second ring and third ring, is use 3D print, because you can do 100% infill with it, with nylon 6/6.
Ah, okay.
And then also, one of the things I've learned about this is charging it negatively, not positively charged plastic, but negatively charged before you put it into the model. So that's one of the considerations we're doing, is to charge it negatively as it comes out of the 3D printer. So it's kind of like as it prints, it's ready to go. Instead of charging it or decharging it, negatively charging it afterwards, doing it as it's printing.
Okay, so there are some technological advantages. And actually, I see the 3D printer behind you in the background. It's behind the SEG.
Use it all the time, yeah.
Yeah. So there are some advantages. You're picking up stuff from new tech that you're able to apply and basically just make construction of this thing a little easier.
Yes, and technology for like readouts and electrical equipment back in the 60s, 70s, 80s was vastly expensive, as compared to now you can get it far cheaper. A lot of digital things that we have now, they didn't back then. These didn't exist back then at all. The oscilloscope certainly did, but not to the point like we have now.
Yeah.
They're much better now.
Well, and for stuff like that also, if you pick up stuff from that era, you can get a discount getting it used, right?
Oh yeah. Yeah, it's kind of some of the fun stuff is back then, like the pulsars and the AC equipment, the DC equipment. It's old school, so it's a lot less digital. So yeah, I like getting my hands on that if any of it I can. It's great stuff. Such as the capacitor bank for charging, and it's right behind you. That one's a scratch-made product from a company that doesn't exist anymore, and it's like 1990s technology.
Oh, okay.
It's very old school, just hand put together components, nothing really digital too much at all, but it does a job. It does the job I need.
Amazing. Well, Isaiah, in terms of magnetization for rollers, was that everything you had, or?
What's some better samples? I need to find them and show them, because that's not like all the samples. Oops, this is not my phone. Sorry. I'm too used to my own tripod being around here. I want to show some better samples and clearer waves that I've done. That's it. Most of them were mounted on those wheels. Yeah, so this is one of the next ones I'm doing. The next trial is not only just putting the wave on the surface. This was 3D printed to do this, but putting the sine wave impression on the surface, but also on the inside.
Okay.
To kind of compress it. The ultimate version of these rollers will probably be much thinner rings, such as these ones I have. I just got these as samples, but they're much, much more thinner. These are actually the correct weight. They're right at about 10 grams each, and that is ideally what I'm going for. So that the copper band be 7 grams, this would be 10 grams, the Teflon would be 4, and the neodymium 13 equaling 34. So these will probably be the final product eventually, but right now I'm just working on all the surplus magnets I have and making all the errors and working all the bugs out of the system, which is this size. The other one with the, yeah. So this is one of the forms I use just to kind of see if it even can be done, but you have it builds up, the ring will fit, if I get one out here. The ring will basically fit in here. This is not with a jig, of course. The jig will come later. But basically the current comes in here as long as like this is north facing up. The current comes in here, builds the field up, and then drops it down, and then it circles back around. So as it's rotating, the field is going up and then going down and going up and going down. But ideally, it would have a jig that would fit over it that would have, like, instead of 34, it would have 136 points.
Okay.
And you would, I did one experiment and it semi-worked, so I run current one direction and then in a parallel coil run it the other. So with that, the current would, on this one would be going one direction while the current in this coil would be going the opposite, thereby creating multiple tiny little spikes. So that'll be one of the upcoming experiments, so that basically this one big loop of magnetism would have 136 tiny little ones.
Okay.
A subcarrier, essentially. Let's see. I know there's some better ones I wanted to show you. Oh, and then this here, I wanted to show the leapfrog effect. And so that's south up. Oh yes, here it is. So this is one of the things I was looking for and can make happen with the special magnetizing process with one point. Let me get that magnet film so I can show you those fields. This is a brand new piece of film, so it's much more clear. So this is one that has like the 34 points in it. And this is one that was the very first trial run on the ceramic, and this is, you know, I tried these at like 1500 volts, then went down by half and half and half. Eventually found 250 volts was the optimum. I think this one's just a normal ring with no impressions. And then this one has, this is the one we did the readout on. This one has the side blip, which I'll show you here. So it's that like square wave. But what this causes, let's see, I'll go for the normal magnet first. The normal one just pushes. Not much of anything happens here. But when you get this one, you get this nice spring effect.
Here, let me focus in on that. Can you demo that again?
Yeah.
And again, this is a result of the fields that are magnetized into the rollers.
Mm-hmm. And it's only on that point that I put a big square right now. Some of the rings I find when they do this, and I can't get it on demand, but I found sometimes they will just vibrate for about a second. Instead of rolling like that, they'll sit and vibrate. I might be able to get one of those to do it. But yeah, it has this springing, jumping motion. So that is one of the attributes I'm looking for. I've seen that in Fernando's rings. When he would magnetize them, they would jump ahead like that because it has that big peak and then a drop.
Yeah, and again, one of the takeaways is the Searl Effect Generator is a lot more complex in ways that are not immediately visible.
Correct. And that, like that full jig I showed you with it starts at, and it does a 180 degree turn. So with each one of these little points, you would start basically, let's say at 12 o'clock, and then when you get down to the 8th bottom one, it would end up at 6 o'clock. And so those jump points would make a whole full 180 degree rotation. Let's put this here. So this is, you know, this is the one. This has 33 points on it, and it really doesn't do a whole lot. It bounces a little. This was one of the first trial runs with one of those jigs that blew up. So it's interesting. Now this is a ceramic, so it's not as strong as neodymiums. So you get a little bit of a bounce, and that's mainly what I found is because Like in the dream, Searl told me leave one empty, so I left one empty. There was no wire going through it for the modules. There was one empty spot, and that one empty spot acts as the spring.
Ah, okay.
Yeah, so that was one of the discoveries only because of that dream I had with him.
Well, it is interesting to see how much stronger the neodymium magnets are than the others.
Tremendously. The density is, like these are like 4.5 GCM/3 squared. The density, and these are 7.45. So it's not quite double, but it's quite a bit more dense. And I know that firsthand for magnetizing and also drilling into these, cutting and drilling. It's a whole nother story. Let's see, oh, I'm doing the wrong one, not that one. Yeah, this one. So this was one that was kind of the flop, but it had some interesting attributes. So I don't know if it'll vibrate for us or not. Yeah, maybe not. Kind of acts just like that one does. But this was just the test example. It used to do some vibrating stuff. I guess it's not going to do it for me. Yeah, sorry about that. Yeah,
There we go.
Yeah, that has a nice spring effect. All because that one empty point. It's definitely not as pronounced as neodymiums, but they're substantially stronger. Shoot, let me get that. So one of the things I've been learning because of the research with Floyd Sweet, Searl talked about it a tiny bit, but Floyd Sweet and people that followed him talked about it a lot, and how to do it is not just putting the patterns onto the magnets, but also conditioning them with high voltage and treat them as though they are a dielectric.
Okay.
So that's something very new, and I just, like yesterday, started doing experiments, and I haven't had any positive results to show you all, but that is another thing that Searl mentioned a few times, but it was he hardly ever talked about that aspect, but it was a critical part with getting these magnets to operate, is treating them like a dielectric, charging them with high voltage. And I mean, it's something I never really heard until very recently, and I kind of think like, I mean, it's a brick of material. It's a ceramic material. How could you charge it with high voltage? Would do anything. But other researchers that I've followed have used high voltage treatment on ceramic magnets, and they have produced magnetic bubbles. And when they put their magnet film up to it and they move another magnet around, it doesn't do it on these, but they can get their fields inside those magnets to move. And
okay.
It was just weird. I have yet to see that. The best I've seen is sometimes when I've blown holes with magnetic fields, I can put the neodymium inside and then use another magnet, and it will shift the magnetic field around on the inside of right through this into the center.
Oh, interesting.
So it's a little odd, but that's not like the material shifting. It's more like it has a little hole between the magnetic field. That's the best I've seen personally. But that's another area that is vastly important for this to do anything like Searl claimed he could do, is condition the magnet with high voltage. So I've been doing high voltage, DC high voltage, also using a small Tesla coil, this one here. So far I haven't had any results. I mean, this is just a $30 one from eBay. But I also tried some higher powered DC, let them soak in the field, and so far no results, but I got the custom made Van de Graaff generator. I'm gonna be doing experiments. I'm going to keep going and going and going and doing it until either I find something or I just know there's nothing to be found.
Yeah.
But the thing with me is, I mean, sometimes it takes months and it's one tiny little tweak and then I get results. And I've had that with this thing. It took me forever to get it to work, and it was all because I used one type of wrong plastic.
Well, it seems like with the roller magnetization, you are still kind of in learning and development mode, right?
Yes.
So.
Yeah.
Yeah, so it's just, keep working with it and see how it goes. And, again, the thing that blows me away is how much more complex the Searl Effect Generator is than I imagined, than most people know, right?
Yeah, and like I'll keep referring back to this because it's such a good example. So this is, builds the amplitude, and so when it relates to the magnets on the stator, what I found, for at least for now that I understand, is each stator magnet, there's about 6 magnets I'm going to do for one stator on the first ring. Each one of those segments needs to have basically a peak and a valley in the amplitude on the field, and then it's interlaced with the tiny little wave, just like the roller does.
Okay.
So kind of like how the roller will have like one segment will have a peak, and then it just goes around, and then a peak, and it goes around. That will be similar, but on a much more larger scale. And it has something to do with the interaction of how that field wraps around. I still haven't got to that point because I haven't built jigs for that yet. So I'm just perfecting these guys. So once these are to my satisfaction, then I'm going to move on to magnetizing the stator. Magnets.
Okay.
Yeah, I have done one trial run with the stator, and I know I can put fields on them. So I know how it works. I know the direction of the current. It's just I need to do it at a very precise level. So we have 3D printed jigs. You can just slap in a stator magnet, and you get your beautiful patterns.
That's amazing. So again, this is in progress. This is something that you are currently working on. We don't have a final product yet here, but you were moving forward with it.
Oh, yeah. Yeah, this is all these iterations. This did a couple, I think this worked twice, and then it shorted out. And so I went from here into this version. I thought a steel core would amplify it and help it. Essentially, with all the patterns I saw, it did nothing. So I went to this, and I just made a plastic clear core in there, and I get these beautiful rings. So it doesn't seem to matter that you do a steel core or not. In some ways, this kind of looks like those Rodin, I think it's Rodin coils, if I got the name right, where they do the spirals, and beautiful spirals. You could do multiple points.
Yeah.
So when I built this, I realized it kind of looks like their system, but theirs was never intended to alter or change or magnetize a magnet. So when I built it, I realized like mine kind of looks like theirs.
Interesting.
Somewhat.
Yeah. Well, and I know the Rodin coil has its own mathematical basis, right?
It does.
Marco Rodin came up with that. So
Yeah.
yeah, that's intriguing. Maybe there's some overlap there, right?
There is. And I mean, when I first built this, I was like, oh, it looks like the Nautilus shell, or one of the spiral of the shell from one of the ocean creatures. I think it was a Nautilus shell, but the spiral was similar. That's what surprised me. It's just kind of finding these things that are very surprising. Now, these were all the test runs I did with lower voltages, higher voltages, and I got some really crazy effects on some of them.
Can you demagnetize those and reuse them, or are they toast once you've?
Yes. These can be reused. I would set them in my sintering oven, heat them to about 700 to 800 degrees, wipe the field. So I have a guy in Clackamas who has a full big magnetizer system, and he has helped me quite a bit. So I could take these all and remagnetize them.
Oh, cool.
Yeah, and just put fresh new fields on. So it's basically like it's just erase and then restore.
Okay.
Yeah, it's like this one was 3.9 kV, and some of the fields come out really good, and others get really washed. This is 3.9 kV. So some of the fields are really strong, and others were just fragmented. And you can see it's pretty lopped. I wasn't very happy with it. But when you start getting these really high voltages, it's 3.8, high 3 times. Yeah, see, it gets really loopy when you get those high voltages. It's not symmetrical. So I started backing down on voltage and brought it down and found about 2800 to 2900 volts is really key for this size. And I think it also has to determine what the amount of wire you have you're going through compared to like maybe 10 inches compared to 12 feet. You'll have different voltage ratings.
Oh, okay. I get what you're saying.
Resistance in the wire.
Yeah, and again, it reminds me of, actually that reminds me a little bit of a transistor, right? They come off of that dye machine, they all look beautiful, but some of them work, some of them don't.
Right, yeah. So far this one has held up. I think it's because the resin is protecting everything in there, and there's no physical direct contact with the magnet, which is, I found, if you have a paper thin space between the magnet and the coil, you're fine. These are very electrically conductive, so just even if the wire's right up against the magnet, after a few times, it'll just blow a hole in the magnet and the wire, and you're done. So try and keep that paper thin space is real critical, and that's what these jigs allow me to do, is keeping that wire real tight at the right geometry. One of the things I learned with this, if I got, let's just say for instance, if I got the wire and held it 90 degrees, no pattern at all. If I go this direction, no pattern at all. But when you start going to 15 degrees, 20 degrees, I tried 45 and it just lost it. It would just start to get screwy. So between 15 to about 35 degrees of arc or angle, you get some real nice concentric patterns.
Okay.
And that's why that's what I saw with this, is 21 is a prominent number in law of squares. So I'm like, you know what, it's not 20, let's just go for 21. And it also ends up being, when you do 34 points, 21 degrees, 8 layers thick, you get a perfect 180 degree rotation. If you change one number, it won't work at all. I think that was it with law of squares. Yeah, that was it. So let's see. Showed that, showed this. Oh, this is something I just started working with yesterday, and I could probably hook this up and show you, is finding the resonance point on these magnets. I knew eventually I would have to find it, but up until just a few days ago, I had zero clue how to do that until now. And this is thanks to the videos I've seen on Floyd Sweet, and Tom Bearden worked with him, John Bedini worked with him, and numerous others. But there's a few examples given of finding those resonance points. So I put together several electromagnets, and even a smaller one, and then this big coil, because I wanted to like start off like, okay, let's not just try it with my system. Let's kind of try something that was close to his. So I got rectangle magnets and was able to get it to fluctuate and find a resonance number, Hertz response is probably a better word, of these magnets. And what I found is with the ring magnets from the company, 18 Hertz seems to be a pretty standard. Between 18 to 22 Hertz, it's real responsive. Now with one of the magnets I have, I think it was one of these. I think it was this one. In one of these, I found it responded at 30 Hertz. So I was able to change the Hertz response in relation to its, this one this one's a pretty clean one. The nice fields. I'd set it in between one of these fields, and what I'd do is basically I would set it, this took quite a bit of trial and error yesterday, but I'll just show it real quick. We'd set it basically like this, and using the voltage was not as critical as the frequency. I could get this to do it at 6 volts all the way up to 20. But basically, when you tune it just right with just the right frequency, this razor blade will just oscillate and vibrate back and forth, kind of just like that.
Oh, okay.
I'll probably do this a little later. We can photograph it. I'll show you. It takes a little while to just fine tune, but there is a fine tuning. But once you get that, you can find the resonance points on these magnets. It was very exciting to find that.
That was cool.
And then with the system I'm doing, I found I actually change it. So what I'm really trying to change is the Hertz response to 136 Hertz. That way I know I've set this sucker to be 136 Hertz, not just because I see it on the oscilloscope, but this is resonating at 136 Hertz.
Yeah, and you are digging into this stuff. That is what is so cool, you know?
A scanner of sorts. So I was talking with Josh last night, and I'm going to come up with something to where it's going to be a 3D print, the movable 3D print. So basically you can put the magnet you need into the fixture, have a custom made coil underneath, and this one needs a little soft foam underneath it for it to do. If you have it right on the magnet, it won't work. Or I should say the magnet's right on the coil, and this, which originally I thought nothing will happen. But if you had like a spacer of some sort to hold it off just a little bit, you could find that resonating point.
Huh, okay.
So it's just kind of like trial and error, but the thing is, I want this to be what other people can follow my work and do it and find more things than I have found. And one of those aids is 3D printing. Is I can make these files, somebody can print out, do their own experiments. That's one of the the goals of this whole project, is others can follow my work very easily if they're even interested. Such as those 3D print jigs.
No, that's wonderful. That's wonderful. Yeah, I mean, you're resurrecting something that was very nearly lost, right?
Almost
and so
lost.
it's amazing that you're making it accessible for other people. That's so cool.
Thank you. Yeah, it's exciting because I want to share this information, and I'm not one to just keep it all locked away so nobody ever sees it. That's why you're here, because I want to show this.
Yeah. Well, and thank you for having me, man.
Oh, you're welcome. So let's see. So it's finding the resonance points, and the one thing I found, at least yesterday working with this, I worked for this for about 4 hours playing around with it. The neodymium magnets are going to be a little trickier, and I could not get a frequency response on any of the neodymium rings I tried, and I think it probably has to do with, this is just a razor blade I found. The smaller the better, the easier to oscillate, but you're dealing with much more powerful fields, so the frequency response is definitely going to be different. But as I play around with it, I know eventually I'll find either I can get those things to respond or I won't. But with the ceramic ones, I definitely can easily get frequency responses from them. Ultimately, it'll be a system kind of like, you put the coil into a sealed chamber like this, and then put the magnet and then the razor blade on top.
Ah, okay.
So that there will not be any wind interfering with your patterns. It won't be this, because this is a scale.
And again, the goal is to kind of mass produce these in a way.
Correct.
Because you're going to need a lot of them, and if you build multiple SEGs, multiple ring roller systems, then you're going to need lots and
Different
lots of
sizes.
stuff.
Yeah. Oh, speaking of different sizes, so this is something I'll show you here. This is something I'm working towards. This is going to be the stator on, I just call this the half scale model. It is, because there was a variance with the roller sleeves, I had to make this one precisely 51.125% smaller than this system here. So it's not exactly 50%, it's like 51.125 or something. It's dang close. But that is, before I build the second and third ring stage of this, I'm going to be building this one. I have all the rollers. I bought all 66 rollers rings.
Oh, wow.
For this full system, so I have all of them. What I looked through financially is the cost is about a 95 to 96% cheaper in cost to build a half scale model than a full scale model.
And again, from what you mentioned earlier, the law of the squares holds as long as you reduce everything the same way, right? So.
I hope so. What I've seen with others they've done some replicas of Searl's work, and they didn't follow law of squares, yet they still had results.
Okay.
Mr. Delphin had the extreme cooling. Roche and Godin, that cooled the whole warehouse down that they had the thing operating. It dropped temperature down. They had amazing aurora effects. So I figured, like, nature doesn't know that I'm using a 50% reduction.
Yeah.
So if I just keep everything the same, but just reduce it 50%, let's just see what happens. So I got all the copper, enough to do all 66 rollers. These are just the main tubes. And then let me get these right behind you. I have the roller rings, which they're very cute. These are enough for all three layers, all three rings. So they are all exactly half scale size. So there will be 8 of these per roller. So you get these, from half scale of this down to much smaller. This will be the outside copper layer. But propelling them, driving them like I drive these models will be a cakewalk compared to driving these heavy models. But that's this is perfected. So basically it's kind of like working on the magnetic fields and also completing this one, building 3 full functioning rings. And the real trick is going to be able to get the tiny, tiny fields that I want to put on here even tinier onto these tiny, tiny little rollers.
Yeah.
I believe it's possible. It's just experimentation, ingenuity, creativity, and eventually we'll find a way.
Well, and making the smaller scale model, it seems like that has so many short-term advantages, right? And you can always come back to the larger ones. You still have the tools and equipment, and you've got all the stuff in place for that. And so you can do this learning process and develop and adjust and then reapply that to the larger one if necessary.
Correct. And the nice thing with this is financially, what I've calculated is about 95% cheaper. Literally, it's crazy cheap compared to these big models. So that's one of the advantages, and the things I'll work through, all the technicalities and the bugs in the system, so to say, that I'll be able to work through in this small scale model. So when I go to do this second and third ring, I'll have kind of broken the groundwork of what to do, what not to do. This was made about 14 years ago, and I never went anywhere with it. So this is my first attempt at a second ring. It was at the time I thought it was a great attempt, but looking back, it was just bare bones basic. But this is just acrylic glued together, ceramic magnets I hand ground in place. I had this done by a company in Tualatin. They did the copper band for me. Did a pretty good job. So that one actually I found now is way oversized, and with Josh's help understanding law of squares, we've come up with formulas to be able to find out, like, literally right down to the thousandth of an inch accuracy for these layers. So it's very exciting. And even a third scale, like you'll have, I'll go here, you'll have the second ring and a third one. The third one will only be about, if with the rollers, about this wide. It won't be much bigger than this. And then you have to add the inductors to it, which these are inductors, the first trial run of inductors. So I really thought with a third ring it's going to get pretty big, but it's really not. I think about 26 inches is the, with about 29 inches once you get the rollers added to it.
Amazing, amazing. Well, Isaiah, thank you. Thank you for the ring walkthrough, man.
You're welcome.